Hello everyone, thank you for joining us here today on YouTube Live for our webinar. A little background on where the idea for this topic came from. About a month ago I was out in the field at a place called Treasure Island in the San Francisco Bay. Many people know it who drive across the Bay Bridge between San Francisco and Oakland. There's actually a site out there that we like to fly at. We were out there one day testing out our LiDAR system as well as our backpack systems, and I noticed when I got back to the office that the UAV LiDAR data collected the areas on the tops of the buildings and the canopies of the trees extremely well, while it missed some of the sections of the point cloud that represented the facades of buildings and the undersides of trees. Whereas when I inspected the live backpack data, I noticed that the backpack or the mobile LiDAR system was able to capture not only the undersides of the trees and the sides of the buildings, but it did it very well. And at the same time, it missed the regions of the point cloud that were in the uppermost canopy sections of the trees, as well as the tops of the roofs. So I had this idea to use LiDAR 360 and a tool in it called the rectify tool to align the tool data sets and thereby remove the data holes found in each of the separate data sets. I then merged these two data sets to create a single point cloud that was spatially coherent in the sense that all objects almost had full coverage of LiDAR data. I was very impressed with these results and decided to post it on my LinkedIn page, and then we posted it on the company's LinkedIn page, and it received quite a good response. So we went ahead and gave the people what they want, and we wrote the article, which Kevin mentioned earlier, which is now featured on our website. And then we thought to actually do a webinar for you today, where I'd actually show you how I went about doing it and give you a little more background on what data holes are, how they come about, and some of the benefits that may be not so obvious of using LiDAR 360 to align data collected from multiple platforms. Now, for those of you out there who don't quite know what I mean when I say data holes are regions of a point cloud where no 3D data exists. They occur where an object or surface with a mappable spatial structure can be found. However, this surface was occluded from the surveying instrument or instrument's field of view during data collection. Information gaps of this type can present troublesome or debilitating quality issues during the development of project deliverables or the running of operation that make use of laser scan data. I should also mention that all laser scanning platforms have limitations that can lead to the formation of data holes. For example, airborne and UAV LiDAR point clouds often lack measurement data in the sub-canopy regions of forested areas that can preclude these data types from use in the determination of stem diameters and canopy base heights. And these individual tree metrics are key to estimating timber volumes and biomass using allometric equations. Conversely, however, ground-based terrestrial or mobile LiDAR systems capable of capturing the tree stems and forms can miss the top sides of forest canopies and tree heights. These tree heights are also key attributes to have when deploying many forest inventory, growth, and yield models. I think we could keep going through and come up with many more examples of where not having sub-canopy information or not having information about the sides of buildings can be particularly troublesome for users of LiDAR data. I'm now going to launch into providing you with details of how you can actually go about using the rectify tool in LiDAR 360 to co-register two data sets to fill data holes. In this slide here you're looking at is actually the outcome of a co-registration process that was performed in LiDAR 360's rectify tool upon two data sets that you saw in the previous slides in order to fill the gaps in information and produce a LiDAR data set for a forest that then can be used to extract out all pieces of information needed to predict volumes generate high-resolution terrain models, or perform a variety of other functions which make LiDAR data valuable to people in natural resource management. So you now see I've launched the LiDAR 360 project window where I've loaded into it 2 separate point clouds. The point cloud that's on the left was collected from our UAV LiDAR system, LiAir, and the one on the right was collected from our LiBackpack system. These data sets were collected at Treasure Island, which is a site I mentioned earlier in this webinar. So what I want to do here is I want to georeference the LiBackpack data using the UAV LiDAR data. UAV LiDAR data has been PPK corrected using base station data and onboard GNSS information, whereas the LiBackpack data has no global coordinate system assigned to it and is in local coordinates. If you didn't know this, you could always go up to the actual point cloud file name and you can right click on it. And when you do this, there'll be a set of options that will pop up. And the option that you'll want to choose is Info. The info will tell you a lot about the point cloud, including the global coordinate system that the point cloud is referenced to. You see here that this UAV LiDAR data set has been georeferenced already to the WGS84 UTM Zone 10 North global coordinate system. So I can close out of this now, and I'm actually going to now launch the rectify tool. First, I must decide that which window will be my reference window. Since I want to reference the backpack data to the UAV LiDAR data, I'll keep these as is. And then I will click the binding button, and you'll see the rectify tool will pop up. Here, there's a few options. You can either use spheres or pick points. Since there's no spheres laid out in the scene, we'll pick points. And I'll zoom into my scene, and I'll start to find matching points between the 2 point clouds that I'll then use to build the transformation equation that will shift the point clouds into alignment. I like to use the corner of buildings. When you want to add a new point, click the plus button, and then zoom to another area in the scene, and find another set of matching points. It's good to disperse your points throughout the scene, because if you cluster them all into one side, the actual transformation will be biased, and you may see a good fit in one area of the point cloud and a poor fit in others. So what I'll do is I'll go over here and select another one to serve as my second point, rather than picking one so close to my first point. This can take some time, so be patient. Here it's very important to make sure you're selecting co-located points between the 2 point clouds in order for the outcome to be optimal. You'll see here the rendering display is turning in and out. But with a higher performance machine, you should be able to visualize all points continuously. Now that I have my second point, I'll have to find a third point. So I'll click the plus button again and search around the scene for another corner of a building that I can use. Perhaps I'll go back to where I had the second point. Oh, I missed. This is an important thing to note. Always tilt the point cloud up towards the sky so you avoid clicking points that are located in the background. Now, you need at least 3 points in order for LiDAR 360 to calculate an error. You see once I have 3 points, error metrics start to show up here. What this is the residual distances in the X, Y, and Z axes that remain between the 2 points selected to do the alignment. I'll choose a fourth point to show you how you can essentially choose different subsets or different combinations of pick points and reduce your overall error throughout the data set. This can take some time because you'll have to manually go through and toggle on and off the different combinations to find the lowest amount of total error possible. But doing so will allow you to yield the highest possible quality results. Let me now click around and figure out what the lowest possible combination could be. It seems like point 4 has quite a bit of error in it relative to the rest, and I see why now. I missed finding the exact corner of the roof, so I'll reset my position of 3 and then recalculate the errors to find the lowest combination of total error. which is simply the sum of the error column. After clicking around for a bit, I've decided on choosing point pairs 2, 3, and 4. I'll then click the small transformation button and save it to my target directory and click apply after hitting save in order to run the transformation tool. This should finish fairly quickly, but depending on the size of your point cloud, it can take longer. Once this is done, you'll have to reload in the transformed point cloud. I recommend using an iterative process to actually go through this, where you fit once and then align the point clouds, bring them in, and then start the rectify process again. After 2 or 3 times, you'll see your error start to stabilize, and you'll know at that point you've achieved the best possible fit using LiDAR 360's rectify tool. I should also point out that you may want to save these point matches in order to run the process again. You can do this by clicking the small save button underneath table and then save in an ASCII text file for later. Here you see I've matched point pairs from the first time I did this registration process and the creation of the article upon which this webinar is based. Okay, what I'm now going to do is remove the LiBackpack data set that I used to do the first round of rectification in LiDAR 360, and I'll load in the result. This is the one that's been transformed based on the matching pair of points we found. You see here that while they show up in generally the same space, there's still some problems with the alignment. The area in white-ish gray is the LiBackpack data, while the area that is colored from blue to red based on maximum minimum elevation values belongs to the UAV LiDAR. You see that in portions of the alignment that the gray area sits well above the area which is colored, or the UAV data. This represents a poor alignment, meaning we should probably go through the rectification process again, choose new matching point pairs that will give us a better understanding or a better alignment between the two data sets. I'll open the profile tool just to show you a little bit more by what I mean poor alignment. When I draw a fairly thin profile, this one being only about 1.3, 1.4 meters, I see that around the buildings which I used as matching points, there's fairly good alignment between the data sets, but as I move away from it, the ground planes diverge markedly. You can also see here on this tree that the gray dots and the colored dots do not align very well. This makes me realize that while I did achieve good fit between matching point pairs for the sets I used, globally there's still a lot of error in the registration between the two data sets. So what I'll do is I'll open up 2 new viewers, and I'll place in the first viewer my UAV LiDAR data set, or my reference data set, that I will then find matching point pairs in with my data set to be aligned, or the result of my first transformation of the LiBackpack data. I can actually click the Link Viewers button here, select the 2 view screens, and then add them. Click Apply and make sure the crosshair is clicked so that I can zoom in to different areas of the point cloud to see exactly how close the two have been aligned within the same coordinate system. I choose this small area on the back of the fence. You'll have to kind of click in both windows since there's limited rendering capabilities on your machine, or on this machine I should say. And I basically tried to look at specific objects or easily distinguish objects, such as the corner of this fence, and see how well they're aligned. I actually want to switch to orthogonal perspective as well. This allows me to avoid any distortions caused by the perspective view rendering. So I move it about the screen here and just check some areas, and this gives me an idea of exactly how well the 2 data sets have been aligned within the target coordinate system. I could check the backs of cars, or basically any easily distinguishable object within the scene.
I'll launch the rectify tool again in order to find new matching point pairs. Remember, the reference data set is the UAV LiDAR, and the alignment is going to be the live backpack data, which was the output of the first pass of the input data through the rectify tool. I've already found matching point pairs that produce a very low error, which I'll now load in. I had saved them out earlier as the ASCII text file, but I can now open it up and import these as the matching point pairs. Click Open, click Yes, and now here you see in the viewers the locations of the 3 matching points used to perform the next round of rectification. Here I've selected an area that's a light post on a utility pole. I've selected the corner of a chain link fence. I can switch to the pan hand mode here to move about the screen a little more easy. Since I've already tested these values and I know that they'll produce a better alignment between the 2 data, I'm just going to click the transform button and apply the changes to produce a new data set from the live backpack data, which should have a better fit with the UAV LiDAR data. The status bar at the bottom will let you know how far along in the software is. This can take a moment, so give it time. One thing to keep in mind here is that we do recommend you use more than 3 matching point pairs when aligning 2 different data sets using the rectify tool. Our developers generally recommend that you use at least 4 sets of matching pairs in order to avoid creating unnecessary bias in the transformation equation. Once it's completed, you can click Yes to add the output to the current project. I'll now close out of all my viewers as well as the rectify tool by clicking the X button in the upper right hand corner of each view window. To avoid confusion, I'll also remove the result of our first transformation or application of the rectify tool so that I now only have the output of the second application as well as the reference data set or the UAV LiDAR data set. I'll add them both into the same viewer to inspect their alignment. Here I see a lot of good things. First of all, I see that in the areas where there's bare ground or areas with just very small amounts of cover such as grass, the gray and the blue dots tend to occupy about the same plane in any local area. Here there's a slightly higher density of gray dots, which could represent some misalignment in the data, but is still far improved over our previous result, or our first hash for the rectify tool. To get a better look, I'll launch the profile tool. I'll increase the lower size of the bottom window. And then I'll draw a profile line across areas which are flat, as well as some of the buildings and tree objects. The trick is to make sure that you get in an area of the roof where you're not cutting off any eaves. So you just have a nice clean vertical profile of the data set. What I want to do is adjust the display properties next of the live backpack, the transformed live backpack data set to make them easier to view. To do this, I will select to turn my UAV data set into RGB, which is available because our LiDAR system has integrated color camera sensor, and that photo information was then fused with the individual LiDAR point cloud during the georeferencing step of post-processing. We'll also change the color of my live backpack data, something that stands out against the natural palette of the scene. I'll choose this deep red. Click OK, and now you can see the line, or the deep red points that represent the live backpack data, which was aligned to the UAV LiDAR data set. What I like is that the UAV LiDAR data set, or the true color points, are somewhat normally distributed about the live backpack data. This means the live backpack data forms sort of a central tendency between the spread of points belonging to the UAV LiDAR. As you move away, you see some drift where the UAV LiDAR does not fit the exact center, the live backpack is not fitted to the exact center, but the alignment is much improved over our first go at it. For the sake of this demonstration, I'll only apply one more transformation behind the scenes in preparation of this to give you an idea of what the best possible output could look like when time is taken to run 3 iterations of the rectify tool. I just want to also inspect the data real quick here and point out a few things in it. I'll turn on my iDome lighting and color both data sets using the elevation palette. You see here above the roofs there are some noise points. These can be cleaned out in the post-processing procedures using LiDAR 360's outlier removal tool. I also want to remove some of the anomalies that are created, or I should say non-target data, by people walking around the scene while the live backpack data was created. I'll do this also using the classification tool to manually identify points representing people, assign them into a class, and then drop them out. This step will be skipped here in this video. I'll now add the result of my third application of the rectify tool, as well as the result of my data set cleaning, which removed some of the error points as well as the points that represented people moving about the scene when my live backpack data was collected. Once again, to avoid confusion, I will remove the output of the second rectify. So now all you're viewing here in the window is the outputs of the third rectification application, as well as the UAV LiDAR data. When I turn on the RGB color again for the UAV LiDAR and keep the height palette colored points of the live backpack, I can see there's a few advantages of fusing these two types of data set. For example, between the time the UAV LiDAR data was taken and the time that the live backpack data was taken, a fire truck had moved into the scene. You also see that the UAV point cloud data has less dense points around the power line features. It's often of great interest to city planners and asset managers as to where the power line or overhead utility structures can be found in the scene. I'll cut one more profile view and also point out to you that after this alignment, the tops and the bottoms of trees, or the tree canopies, are also fairly well aligned. Let's zoom in here and change the point size to be a bit larger, and you can actually start to see that the points from the live backpack are very dense, and the branches fill in as I increase the point size. The walls of the house here are also well aligned with its roof line, and as I inspect the ground, I see that I have maintained a good fit, at least in planar surfaces, between the live backpack data and the UAV LiDAR data. I can select the pan tool, or the hand, from the menu in the top bar, and move about the point cloud with greater ease here, while viewing it in profile view. I'm quite happy with this result here, and it will allow me to move on to the next stage of data processing in many situations. So, thank you all for joining me for this portion of the webinar. In future webinars, we'll explain to you in more depth how to use the rectify tool and spherical targets to align two data sets. We'll also take you through the process of removing noise points and many other things to show you what can be achieved using LiDAR 360 and GreenValley International's LiDAR data collection platforms mounted to UAVs and backpack units. Thank you all very much for being here today, and remember to check out GreenValleyInternational.com for more updates on recent products, as well as news about our events and any future upcoming webinars. Thank you. Have a good day.